So yeah, today's session will be about Sloan Digital Sky Survey and spectral fitting of the SDSS data. So Sloan Digital Sky Survey stands for the SDSS stands for Sloan Digital Sky Survey. It is located in New Mexico, USA. It's actually a survey which is done by this Apache Point Observatory. You can see this telescope here. So these are some of the features of this telescope. So it works on spectroscopic data and imagery data, both photometric and spectroscopic data. And the critical focus of this telescope is in the field of AGNs. So many of the people in the AGN field use SDSS data as well, and also provide the stars, quasars, and galaxy data, right? So this is the kind of survey portal that look like. We will get into this portal soon. So you can just click on this link here. I'll share this PDF with you. So and also share this link here. And so you can just go to this portal and you see there are some features for putting array and deck of the galaxies or any object, and there are some more features like grid label. We will get into this so that we can do some hand-on work. So this on the right hand side is actually the information about the selected object. For example, I have just selected this random object here. You can see these are the array and declination of that object, and the type of the galaxies type of the object is galaxy, and its magnitude in U band is 19.10 19.10, and green is 17.60, and R is 16.83, and so on. So and this is basically the spectrum of the data which we will be handling today. Okay, so yeah. So when we go to the explore session, we have this more information about the object. So we will get into this. This is the interface, how it look like, and this is the optical spectrum information of that particular object. We will get into this because we will be dealing with the FITS file which only contain the spectrum of the data. Okay, so we will be dealing with that. So you see I have given you the crop version. So these are actually some tables which are astro query parameters. We will be dealing that in the astro query session because we will be getting back to this SDSS here soon, because when we will be doing astro query we will be dealing with a lot of these kind of tables. So that will be more exciting actually. So yeah, so this was all about I wanted to tell you. So when you open this R18, which stand for data release 18 from the Sloan Digital Sky Survey, you will see something like this interface. So you can either give array and deck of the galaxies or any object you can search, or you can just drag and find out the galaxy. Let's say I just found this galaxy here. So I'll click on this galaxy. Okay, so it must refresh. It must show the galaxy. I'll just refresh this page once because it must show the galaxy preview here. Okay, I'll just try with the new version. I think that might work. This actually not show that kind of error or bug. Okay, so it's a similar kind of thing. So yeah, now we have this galaxy here. So this is the information about the galaxy. So they have changed the interface just a little. So what I will do is, now you can see I have selected this object here. So where it is. So this is the selected object. You can see on my left there are the information about the object. This is the object ID and array and deck of the object. Then we have these magnitudes and the type is galaxy. So now we need the spectrum of the galaxy, right? So to get the spectrum of the galaxy we have to click on this explore button. Okay, so when I will click on this explore button, oh, service is down. Oh shit. this must not happen. Wait a second. I'll just get back to the older version, and I'll check if that's for. Oh no. Okay. Uh, they are doing services of their web page till the 8th month. Okay, so that will actually create an issue for us. Okay, don't worry. Uh, don't worry, let me check with the older version of SDSS Navigator. So this was actually unexpected because this error is from their side. They are doing maintenance of the site. DR7. Otherwise I have the spectral fits file, so that will not create an issue. Okay, just a second. Otherwise for that time period, what I will do is I'll share my fits file with you. So I have shared the fits file in the this Slack. Okay, so this is the fits file. You can just download and keep it with you. So I'll just tell you from the presentation only how the interface look and how you can just download the fits file. Okay, so basically when you will click on that galaxy, you will see these options, and when you will click on this explore button, uh, you will get this interface. Okay, so there are different these options: metadata, imaging data, optical spectrum. So when we are dealing with the image data, photometric data, when we need these magnitudes and all, then we have to download the fits file from this imaging section, which only contain the photometric data. So when you will click on this fits file, it's just give you the link for that fits file, and you can just click on download, and you can easily download that. So there is nothing complex thing. So this interface is actually under construction by SDSS. So if you want to just check it, you can I'll share this PDF with you. It will be similar. So nothing like that. We will not be messed up if we just get late to this interface. So everything will be fine for that case. The second thing is I will look into the Astro query session, because we will be dealing with Astro query in SDSS only. I'll check that prior if the Astro query is working in SDSS portal or not, because they have made the portal for construction for like till August. So yeah, that was actually unexpected. So for the spectral data that I have shared, it is actually from the optical spectral app. Okay, so when I will click on fits file, you will get that download link, and you can also see from here that it has shown the spectral analysis. It has calculated the redshift 0.09 and the redshift error 1.58, and then we have velocity dispersion 123.26 and its error as 10, and so on. Okay, so these are some of the spectral information that we can get out of from the spectrum. So today what our focus is, we will be calculating the redshift by fitting our spectrum our model of Gaussian profile onto that spectrum. Okay, so I'll try to fix this thing here. I'll try to find the alternative portal, otherwise we will shift to some other survey for Astro query learning part. Okay, so that will not create an issue. I just want to ask you one thing. Are you also struggling with this that the maintenance issue, or just me, or on just mine window it's showing? So this error after clicking on explore button, you just click randomly on explore, it's not showing me anything. So is this for you? Yeah. So okay, so that's from the observatory side, so they are maintaining the thing. So for astro query we will be working with this CAS job. So CAS job is a portal where we can get all the tables, so that's also not working, so I'll find some alternative, or otherwise I will provide you some recorded lectures for that also, for a separate thing, and plus we will be also doing it in some alternative method. We will shift to other sky survey data, but for AGNs, sorry, anyone speaking? uh,
Yeah, so on that website, if on the top left corner you see there's a try new version option,
mhm, yes.
just check that because I tried that. I am not getting this maintenance issue.
uh, just a second, let me just try it on some other. Okay, so it's actually for me. Just a second. So you just clicked on the try new, and so are you logged in with this profile, or you are log out also?
No, I have not logged in yet.
Okay, so did you click on this explore and get that information also? Okay, 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 it worked.
Yeah, yeah, yes,
Yeah, it
yes.
worked here. Okay, maybe I don't know why it's happening here in Safari. Okay, so we are good to go. We are good to go. However, I have also shared that fits file. If you want to work with that fits file, it's okay. So because it might not be the same fits file or the galaxy you select. So basically, I'll just select the random galaxy from here. Let's just search for some nearby galaxy which has the spectrum. um, so let's see this one. Okay, so this is the galaxy, and let's explore this. So once I so yeah, so there are some cases for which the spectral data for that galaxy is not available. Okay, so we can't work on the spectral data for this galaxy, so I have to find some another galaxy. So actually in the earlier navigator, there was an option to select the galaxies with just having the spectral data. So what I will do is, so what I can do is just simply go to that this thing here. I'll just copy paste the array and deck of this galaxy, right? So that will actually work. 179.68. Okay, so there is an option. Okay, just a second, let me shift to this version and just check this. Okay, so the newer version is working properly, but they don't have an option to, just let me check. Yeah.
Modify the RA and the deck are the purple numbers, I think.
Yes, yes, I got that. Yeah. So, thank you. 179.68, and another one was minus 0.45. Why just this happened? So it's a very bad interface that they have made actually. So yeah, I got the galaxy here. So I got the same galaxy here. Okay, so there are some nearby galaxies, you can also work on them. So okay, now what this happened? I don't know why their site is becoming slow. Just a second. 1.968 minus 0.45. Just a second, guys. So yeah, I somehow tried to arrange that green box on this. Actually, on the newer version, they have made the things more complex. I guess the earlier version was very clean and everything was on the main interface. So now you can see that we have the spectrum for this here. So we can just click on this explore button. So you can just if you have a data of area and declination, you can just go to that astro query thing and you can just get all of the galaxies together. No need to just drag and search like this. We will be focusing on that in future shortly. So this is something I was showing you. For the CAS job, you need to first create an account. Okay, so I have already made the account earlier. So I'll log in it afterward. So when we will be discussing about the astro query, so it has a lot of information. So we will be discussing that in future. So now we have this amazing data. We have this image data which contain the photometric data, and these are the bands, magnitude, and their uncertainties is also given. Okay, so the morphology for the from the galaxy zoo is uncertain, so it is not determined properly. So there are here you should focus right now. So in the optical spectrum part, you have these type of things here, and in this box here you will see that you have the interactive spectrum. When I click and open in the new tab, the both one, interactive and analyze spectrum. So okay, so it must be there. Just a second, it was analyze spectrum, I guess. Just a second, it will actually show you the spectrum and you can just visualize it properly. So yeah, here okay, so it's loading the data of the spectrum. So you see it's the same data of that spectrum, and you can just zoom it and visualize it here also. Okay, however we will be doing this in Python, and you can see these are some H alphas and all that stuff here. So we will be actually fitting these two peaks here, and we will be finding the exact value for those. Okay, so these are the spectrum for this galaxy, so you can visualize it and you can just download it from here if you need in the form of a JSON file. Okay, so but right now we will just download the fits file. So actually they have changed a lot of interface right now, so they are trying to do things better. I think they are making it more complex. So I'll just click on this fits file here. So when I clicked on this fits file, I have just this download option here. I'll just click on this download option here. So you see here I have this fits file here. What I will do is I'll just drag and keep this in my folder. It's actually just a second. Where is my folder for third age in school? here. I'll just shift that into this folder. So it's actually the same fits file I shared with you guys here, I guess. I'll just match the ID. So these are plate, fiber ID and all that stuff. So yeah, these are same. So this is actually the same fits file. You can just download it from here. If you want to try something new, you can just download some random galaxy, but I will not recommend it to do right now. Just for follow the pathway I'm trying to do right now. Then you can just try and fit the Gaussian profile over some another star or galaxy to calculate their redshift. Okay. Now, today's focus is to determine the galaxy redshift by fitting a model to the spectral features in its observed spectrum and comparing the wavelength of these features to their wavelength when they were created by the data. Okay. So now I'll just import the functions. So this is the Gaussian profile, Gaussian normal distribution function. So we do this in bachelor's. So everyone must know that in mathematics this is the basic function of Gaussian profile. It's also known as bell curve. So it has a peak and then it is it's a very symmetric function. It has a peak and then it goes down both way. And the thing is it actually help us to fit the spectral. So in the observation spectrums, so we have also these type of peaks, right? So we can fit those peak according to the Gaussian equation, so and try to get the exact value. So first of all, what we will be going to do is just create this function in Python and try to make this work for our mock data. Then we will import the fits file and then we will import this function over that fits file. So first of all, I'll import the modules, import numpy as np. So for plotting the data, import matplotlib.pyplot as plt. Then there is something called curve fit. Curve fit help us to fit the curve. So we will be using that. It's from SciPy. So for that case, you just download pip install SciPy from terminal, or if you want to download from cell, just run this pip install SciPy from cell itself. Okay. So now I'll just I have already imported this I have already installed this SciPy, so I will import the curve fit from SciPy. Just like we imported the fits file from Astropy, like from astropy.io import fits, similarly we have to import the curve underscore fits from scipy.optimize import curve fit. So how we'll do that? From scipy.optimize, so curve fit. Okay. So I'll just run this here. So now, okay, so it is run. So I'll create a function which indicates this thing. So I'll create def then Gaussian, and we have the variable x here, and then we have a, the amplitude, and then we have the mean value, which is the mu here, the center of the bell curve actually, and then we have the sigma value, which will give us the width. Okay. So we will define it as sigma. So you see now how many parameters we have in this function. We have 4 parameters. So earlier we were dealing with either 1 or 2 parameters. So we have 4 parameters, 4 variables here, which will be varying with the different values. So I'll write the Gaussian formula. We have to write this formula in terms of Python. How I will write? I will define a variable which is named as Gaussian, and then I'll write this formula. So I'll define it as a divided by sigma for sig. Now it is multiplied by square root of 2 pi. We know to write pi, we can just write np dot pi, right? But to do under root, we have the similar feature from numpy, which is np dot square root sqrt. Okay. So I'll just multiply with np dot square root, and then with inside that bracket I'll just write 2 times np dot pi. So this is I have written this portion. Now I'll come out of this bracket, and now I'll multiply it with exponential. So you know, for exponential also we have this feature and numpy dot exponential exp, and then minus sign, and then bracket. In the bracket I'll just write x minus mean to the power 2. So there is one more option to write the power, which is np dot pow, POW. Okay, so you can also use that, but this is a very simple option, just 2 asterisk. Now divide this value. So just a second, I'll just create one more bracket here, and now I'll divide. So this is one term, and we have to divide this term, which is again in the exponential, by one bracket here. So it will be 2 times, it will be twice of sigma and its square, right, square. So this is the Gaussian function we have written here. Okay, now just return Gaussian. Okay, so this is our function. I'll just run this, it ran perfectly, so there is no syntax error right now. Now just to check if it's working or not, we have to assign it some random values. So anyone know how will we do and assign the x values? We don't know x values. How will we make use of numpy to assign some random x values? So anyone?
By using range, or yeah.
Yeah, so range is one option, you can do that, but most of the time we use linspace. Linspace help us to actually give more evenly distributed data, but range gave us some particular values, like range 0 to 10, it will give 0 1 2 3 4 5 6 7 8 9. But when you do the same thing in linspace 0 to 10 comma 100, it will give 100 values inside those range 0 to 10. So it is more efficient. So to give some random values in data analysis, we prefer using linspace because it gives us more flexibility. So I will just write here x text. So this will be the test values to test our Gaussian. So it will when we will be assigning some test values of x, a, mean and sigma, so it must show the Gaussian plot. If it will not show this Gaussian plot, then our formula written here is something missing or some having some bug here. So we have to fix that. So let's just write it fastly here, 0 to 10 and 100 evenly distributed separation. Then Gaussian test will be actually a variable to call this Gaussian function. So here the first variable is x, which is named as x test here. So comma value of amplitude, let's say we assign it as 1 here, and we have given it a fixed quantity. Then the mean which will be defining the center of the bell curve, let's say the center is 5, and then the sigma value, which is 1. Now plt dot plot, then what we will be going to plot on the x axis, we need the x test values, x underscore test values, then we will be using Gauss underscore test values on the y axis. Now plt dot show, right? So yeah, our function was right, and this is the Gaussian plot. You can also assign some values like here the x labels and y labels and title also based upon your necessity, but I just want to give you an overview that this is the bell curve, and you see at the fifth value we have the peak here. So that's how this works. And now we will be doing some non-linear kind of things when we have two peaks in the Gaussian, because in our spectral data we might have more than one peaks, which is actually true. In the spectrum we have many peaks, right? So only one Gaussian curve will not work to fit that, because it will fit this thing, it will fit one of the peak, but if there is some other peak here, it will just not fit and go straight here. So that will be very poor pipeline for us. Okay, so we need a strong pipeline, so we will create a non-linear Gaussian. So now I'll create a new function which is actually named as non-linear. So what is a non-linear function? It will be the summation of two Gaussians basically. Okay, so here we will be adding two Gaussians, and we will be adding a continuum to it, and for that case we will be just giving it two Gaussian to be plotted in this frame. So that will help us to fit at least two peaks at a time. So here I will define x value, then for first peak amplitude 1, for second peak amplitude 2, then for first peak mean 1, then second peak mean 2, and for the width let us say it's common for both and the continuum is common for both. Okay, then so basically if you don't know, continuum is the point from where your plot, so it's a point on your x is above which your plot is there. Okay, so it's a point on axis above which the plot is there. Okay, so you see will do when so normally just return to Gaussian 1, which is we have already defined here. So we will be extracting this Gauss function again here. So what it will be doing, x values, then amplitude 1, then mean 1, width 1, now plus the second Gaussian plot x underscore value, so a2, mean 2, and then width 1 plus that continuum. Okay, so this is our non-linear function. So any doubts still here? Any doubts still here? I think we have just created a normal kind of mathematical formula in terms of Python right now, and just we have tried to plot it to check if that was correct or not. Any doubts? If not, just give me a thumbs up so that we can begin. If you have any doubt, you can just speak out in the middle because I am not able to see the chat, right? So yeah, so now we will write x, capital X underscore text because we have already written the small x underscore test. So the new values, let's say length space, this time 0 to let's say 20 with 100 distributions, and then y values is actually the non-linear. We will be calling this function non-linear, and then x values is x underscore test, and we will be defining, let's say the amplitude 1 is 1 and therefore amplitude 2 is 2, and mean the first peak is at 5 and the second peak is at 10, and the width is 1 and the continuum is 1. Okay, so now I'll just do plt dot plot. Now x comma y underscore values, and I have to just write x underscore text as well here, then plt dot show. So you see now we have the double Gaussian here. Okay, so it will be easy for the students because we have already done these things in our mathematical physics classes in BSc itself. So it will be easier to understand this concept. So it's actually interesting when we will be trying to fit a model on our spectrum. Okay, so right now we are just testing out our formulas that it is fitting right, and we have made a multi-Gaussian. Is it correct or not? So now we will be creating a model. We will be trying to fit something. Okay, we will create a fake noisy data. You see, it's not noised. We will add some noise, fake noise into this plot, and we will try to model it based upon the real Gaussian data. Will that fit properly? Will that give the exact nearby values? If that's so, we will try to create a we will try to fit that same model on our fits file. Okay, so that would be interesting. We'll do that now. So now let's try to create a model. Okay, so okay, to create a model we need to create some complex functions, okay, which will contain wavelength, flux, amplitude 1, amplitude 2, mean 1, mean 2, width 1 and continuum. So we will be performing least square fit. So least square fit will help us. It's a statistical function. We know for mean square least square fit, it's try to fit the curves. Okay, so it's a type of fitting. So we don't have to write the big formula for the linear square fitting. We just have already called this curve fit here, so we will be using that only. Okay, now let's see, we define a function def fit, so we are creating a model. Okay, so let's say it's wave and flux. So basically you know, in the spectrum we have a flux value and the wavelength value, so this type of things. Then A2, mean 1, M2, the same thing here, and the continuum. So you see continuum earlier was set as 1, so it started from 1. Okay, so the graph started from 1. So this is the thing. So now I'll print here. So we will be creating a very beautiful structure here. So performing least square fitting. And what if we try to make it more fancy, if that work? Let's see. I think it will give me the error. No, it worked. Okay, so I was just trying to do something. So I was just trying to print is equal to 50 times to make a separation line. So it worked. Okay, so you can do it like this. Okay, so yeah, I'm happy. So we will be dealing with the conventional metrics and optimal parameters. Okay, so these are some new words for you, I guess. Might not be for the mathematical students and the higher physics students. So there are some two things: the optical parameter and the complex this curve matrix, conventional matrix. So we will be dealing with that. So the diagonalization of that matrix will actually give us the error for those quantity. Okay, so we will be defining so for defining two parameters at a time, which is dependent upon the similar parameters, because optical parameter and the convolutional matrix will be dependent upon these things here. So we can define it together by separating it with comma. So which will be like this, and now we will be applying the curve fit here. Okay, curve underscore fit, and then we will be applying non-linear, because the whole matrix will be revolving around this function, non-linear function, which will contain two Gaussians. Okay, so we will be making a model which is actually for two Gaussians, the summation of two Gaussians. Okay, so now the wave, the flux, and then PO is equals to, I'll tell you what I have done: A1, A2, M1, M2, width 1 and continuum. So this is the way that I have defined. The rest of the functions are like this, which will I have defined it as a list. Okay, which is named as P0. Okay, so the parameters. So these are all the parameters for that stuff. Okay, so you can do it like this. Okay, so why I have not done by comma separated values? This is because when I do that thing, it will take this at separately. Right now it will create it as a parameters which are varying. So flux, these and these things are not varying, these are also dependent upon these things, right? If this will change, the non-linear function will change. So this is the thing. Okay, so these are independent of each other, but these are the things which make someone dependent on themselves. So you can write it like this. Okay, so now the error in our model will be, model calculation will be the square root np dot square root. So this is the actually the typical statistic. So diagonal, so to make a diagonal of this matrix you can have to write np dot diagonal, then curve underscore matrix. Okay, then we'll do take this again, and now we will try to print our best parameters with one standard error. Okay, printing best fit values with error. Okay, now how will I print that? Okay, print. Okay, so it's a huge function code, so you have to just write it a lot. So it will be creating our model. Okay, so a1 value, the amplitude value will be plus, so you can plus subtract these type of things here without using that f formatted string. Okay, so it will be like string, it will be a string value with the optical parameter at index 0. Why? So you see that optical parameters are defined here, and at the index 0 we have our first amplitude. So the value we get from the curve linear square fitting for this value at index 0 will be our best fit value, which is defined as a1 is equals to this value. So plus we will add a1 underscore error, and then we will what will be the error will be the error of index 0 for the this curve matrix we got. Okay, so what will be it? It will be something like error 0 index 0, and then so we have to shift a line for the next line. So we have something called /n to make it go to the next line. So let's say I have written something like print hi, then I have written this, and then Jushanpreet, and then I have written something like this t I'm fine. So when I'll just do this, you see when I have written a slash and it shifted that to the next line, and when I have written this slash t, it has given it more space. So these are some of the things you can get to know by time to time. Okay, so I'll just make this as markdown for now, or I'll just delete it. Okay, so why I have deleted this, because it's already mentioned here, right, and /n. Okay, so I think that will be fine to understand. So now I'll just copy this line, because it will be same for all, just the index will be changed. For 2 the index will be 1 and the index will be 1 here, and I'll just write 2 here. Now for the wavelength one, wave 1, which is basically the median, it will be 2, and wave 1 error. Okay, so this will be 3, right? Now wave 2, what will be, it will be 3, 2, 3. Okay, so I have this. Okay, now we will be going for the width. So width is same for both, so it will be similar. So it will be indexed at 4th, and then the continuum error. because continuum also will vary. Why? Because when we'll be adding the fake noise, so the continuum will also have some different values. Okay, so it will shift up and down, up and down, up and down, just like a heartbeat. Okay, so it will be less like that. So continuum level, the index is at 5, and count error. Okay, so this is done. So our value will be printed here. I'll just do one more thing, that I have given a separation line here. So now we will try to plot our things. Okay, so what I will write here is basically plotting the fitted graph, plotting the fitted model. Okay, so the y underscore model, I am just defining it as a name. It will be basically the non-linear model, right? So the y values will be the non-linear values, just like this. The y values are non-linear value, but this time the x will be the waves, and the parameters will be all optical parameters values. Okay, so how will I do that? Underscore this, and then wave. So wave is actually all these values here, and comma. Now I don't have to just go again and write a1, a2, a3. What I can do is multiply optical underscore parameters. What it will do, it will be getting all this list values here only. Okay, at this position. So no need to just go again and write a1, a2, a3. So these are some of the tricks. So I told you there is no need to learn whole Python at once. You just go through the examples, you go through the methods, you learn and upgrade your knowledge time by time, by doing new things, by learning new things, rather than getting stuck on the basic part and doing it again and again. What I did was, I just give you a basic idea of Python, and then I wanted to show you the advanced Python, or the shortcuts of the Python, using these type of examples. So okay, so now we will be creating a scatter plot. The scatter plot will be basically for our data. Okay, and we will be creating a normal line plot, which will be our model data. So our scatter plot will be wave flux, and label is equals to, we will be adding of course a label to make it show properly. So plt dot plot for our model, wave comma y underscore model comma label. So this time, because our it will be our model, so we have this model here, so the y value will be like this, and now the label will be our model, and let's say the color is equals to red. So there are many more colors. We have purple here, right? We have orange, we have Rebecca green, Rebecca red, sorry, and all that stuff. So we have very beautiful colors. You can search on Matplotlib site, so you can just get those colors here. So now we will be adding a line. Which line? Those line will be actually at the cut of the peaks. Okay, it will be cutting them in symmetry from the peaks to get exact value of the peak. Okay, so how we will be using that? We will be adding vertical line. Okay, so vertical line will be for optical parameter, which is assigned at 2 0 1 2 mean 1, and it will be there will be two lines. Of course, there one line will be at optical parameter mean 1, and the other line will be at mean 2. What I am trying to explain is, the mean 1 is at 5, the another mean 2 is at 10, so there will be a line here. Okay, so which will be just showing you exact value. Okay, just like we just draw a line right at the peak. So the optical underscore parameter at 2. Okay, so what happened? Sorry. Okay, so optical underscore parameter and 2 for the first time, and y minimum So the minimum starting is from 0, of course. So these are the value. So you see right now how I am doing this. So the maximum value will be the maximum value of the flux, okay. So till the max peak, so it will be y max is equals to flux dot max. So you see how many syntax I am using right now. We used indexing here to assign it the value for where just a second guys. I'll call you later, Papa. Class. Okay. Hello. So yeah. Now, just a second. We have used indexing here, and then I have given it the minimum from where it have to start the line and where it have to end the line. So this is the function dot max. So it will be finding out the max value for that flux value. Now, comma, there is something called line styles. So it will give you the line style, which is dash dash. So it will not a straight line, it will be the dashed line. So there are two choices. You can just give it something like comma slash this type of thing, right? Yesterday we already did these things. So this is the shortcut to do that, but it will be okay where if you, it is okay to learn something new, that this can also be happen like this. So color is equals to, let's say color is so we chose purple, right? So let's say red color, okay. So and there is something called line width. So line width can be also written as LW, or just you can just properly write line width, and you can assign some number here. Let's say it's default 1 number, okay. So we will give it one more line here. So it's V lines, vertical lines. Similarly you can also plot horizontal line, but right now we don't need that. So I will keep this all the same. What I will do is I'll just change the index number here, okay. So everything will remain the same. So now plt dot legend, why? Because we have used the labels here. So to print these labels we need to show the legend. So now plt dot show, and now we will return optical parameters and curve matrix. So this is our basic Gaussian model, okay. So I'll try to run, okay. So it run perfectly. Any doubt till here, so that we can create a noisy data now and we can move forward. Any doubt till here? Any doubts? Okay, it's fine for one. Okay, it's fine. Okay, so I think everything is clear. So what we have basically done is we have just created this line here. This line is important fitting syntax. So if this is wrong, everything will get disturbed, because this is the line which is determining the optical parameter and the contour matrix, okay. Now wave underscore test will create a test x-axis, which will be again, let's say numpy dot linspace. So these are the x-axis value, okay. Keep it the same, okay. Just name change. Pure model will be the very pure underscore model is the clean model, just like this, no disturbances, will be is equals to non underscore len, then wave underscore test, and let's say first 20, then let's say 40, the mean one is 5, and mean 2 is 10 again, 1 and 0.25, okay. So just assign the random value for those parameters, these parameters, okay. So now we will be adding fake noise, adding mock noise, okay, to the data. How will we will do that? Any idea how will we add noise to our data? Any idea? So we have to add some noise in this model. So we don't have to do anything with the wave test, we have to do with something very variable pure model. So we will be adding the noise with something we have already done. So the noise will be random. So what comes in your mind when you just thought of adding some random noise? So how can you do that? Anyone? So we have actually did that in our previous lectures, but not in that manner. So you have to just do something different. So anything in your mind how we can add the noise using our prior knowledge? Make an array of random values. Exactly we will be doing that. We will be using np.random.normal, and we will be adding that values to our pure models, because this will be the random values. Okay, so we will be assigning a location as pure model, and the size will be exactly same to the pure model. We have to make sure the size of our noise must be equal to the pure model values, otherwise it will give you the error. Now test function, or a noise function you can say, is equals to pure model, pure underscore model. It will be pure underscore model but plus np dot random dot normal, then location is equals to pure model, and plus comma, size is equals to length, which is length pure model. That's it. So this is how we have created a model which will be with the noise. So now we will try to plot our pure test model, okay, which is noisy model. Wave underscore test, the x-axis, and test underscore function, and plt dot show. So you see we have a little bit of noise. Okay, so you see our continuum has a lot of noise. We have noise here, we have noise here, we have noise here. So now our data is having the noisy data. Now the thing is, we have to use this fit function. We will try to fit it. Okay, we will try to find the exact nearby values for these, so that we can fit them properly. Okay, how? We will be calling a fit function now. So out underscore parameters comma out underscore cof matrix, we have just assigned a variable and it will directly show you the answer. Fit underscore fit bracket, we have called those values. Wave underscore test, and on the x-axis we will be having a test function, the noisy one, not the pure one, comma just give it some random guesses. Let's say our initial actual value was around 20, so let's give it some random values, random guesses, so that it can have a guess that the exact value is something nearby. So let's say 19, and then 36 for that, and then like let's say 4, and then let's say 9.5. so since we know those values, we are just giving it a random guess very accurately. But for the spectrum case, we don't know the exact value, so we will be having some critical things there. Okay, so just give those random values there. So when I will print shift enter, you see we have the very amazing fit here, very amazing fit here. So we have the exact value. You see it calculated a1 and a2 very poorly, however, but the wave 1, which was the actual value which was determining the fit, which was the wave 1 and wave 2, are very actually very accurate. You see it is 4.9, the actual value is 5, and the error is 0.00047, which is very accurate, and the wave 10 value is very accurate, 10, and then width is 0.9. so these were the main values we were more dependent upon. So our fit is very accurate, and these are the vertical lines we made. Okay, so now it is, this model is actually ready to use. Okay, on our actual fits file. Okay, so any doubts still here? or just give me the thumbs up. So it worked for you. Nice. Okay, what about Rafael and others? So it worked. Can you put the vline command again? So vline command is here. So what you are trying to say? It's vlines, not vline. Okay. Yeah. So now fitting Gaussian on spectrum. Okay, now we will be having AstroPy with us. Okay, and there is something called signals, which is from SciPy itself. Signal basically help us to detect nearby peak values. Okay, now what I will do is from astropy.io import fits from now I have to write import scipy.signals. We have already installed scipy, so there is no need to do it again as ss, let's say. Now what I will do is no module, yeah, because it's signal not signals, so it will work now. So it's signal scipy.signal as ss. Now what I will do is I'll create something called our sdss underscore data, which will be is equals to fits dot open, and then I will be writing spec the file name, and then I will be doing one more thing, that is sdss underscore data dot info fits dot open. Okay. So now as I told you, the actual fits file, which is the real fits file, have more than one table. Now since it is not a photometric data, it's just a spectral data, you see that our first table is empty. So we don't have any dimensions here, so we don't have any image data. So our first table is empty. The table which we will be dealing with is spec data, which will be containing the spectral data. Okay, so we will be dealing with that. So okay, so I think but right now we don't need all the spectral data. So I think the first one will be fine, where we will get the flux and the wavelength value. So let's try to fetch the data first. So let's say sdss underscore data, and in the first one dot data. So yeah, the first column is flux value, we need that, and there is something called log lam value. If you remember, in our previous session I said that when we were working with the fits file, I told you that there is something called log lam. Log lam is actually the logarithmic values of the wavelengths. So we have to convert those logarithmic values into the normal values of the wavelength by multiplying it by giving the power of whole values to the 10. Okay, so now what I will be doing is I will be writing giving the flux values is equals to this sdss underscore data, then 1 dot data, and then I will be giving a index flux. So I have used two index. First I have given the index of that table, and then I have given the index for that specific column name. So then I have assigned that whole column name as flux. Now I will define the wavelength. Wavelength will be equal to 10 to the power, because we have to convert that log to the base 10 to the normal values, which will be is equals to the same thing here. I will just copy this, but I will change the flux to log lam. Okay, so plt dot figure. So let's assign some figure value. figure size is equals to 12,6 because it's a spectrum, so it will be in the rectangular format and visible properly. So I will be plotting these twos and plt dot show. So where is the error? Okay, so I have forget to apply the brackets here. So you see we have this thing here. So now this is messy. However, we know that h alpha value is somewhere here. Okay, so the peaks are here, but we need a clear footage of this area, right? And this is, there are a lot of noise. So you see our noise was very less as compared to this one, and you see there is a lot of noise. So we just need this portion, these two peaks, and we have to fit these two peaks to get the redshift values. Okay, so how I will do that? We will be doing a cutout of this graph. We will be assigning a range that you have to just print the graph for from around 7000 to 7100, something hereby. So now what I will do that here is sub underscore I will be, it's a subplot np dot where, it's kind of a subset, right? So there is a function which is kind of np dot where, so it will be giving you a range from where you have to start and where you have to end the plot, which will be is equals to wave 1 sorry, wave is greater than, let's say 7000. We'll try to give it a normal guess, I think it will be fine, and using not that and the sign one. Okay, and then brackets wave less than 7100, and then subflux values will be flux inside those range, the bracket, the subset range. Okay, sub I, and similarly the wave value will be inside that function. Now I'll what I will do is I'll just copy this part here and just paste this part here, but I will change it to sub underscore, and the another thing will be sub underscore flux. So I think we did some mistake. Let's take some more range. Let's try to find out the peak. Actually, the wave must be around, so we have to actually get this value, right? So the wave must be greater, its value is actually 25, right? We are just getting these lines here, so we need some lines. Let's start from 710 and let's say 790. Yeah, so actually it was afterwards. So I'll just cut out this value at 730. So you see we have this value here, these two plots here. Now I'll also cut out this value at 75 or 70 will be okay. So 70 will be okay, so this will be fine, and I'll cut this value at 25 also, 225. So you can just do it like this, right? So now we have this thing here. Okay, so this is fine, I guess. Now we will be doing fitting over this thing here. Okay, so now what we will be doing is we will have to find the signals. So we have to assign it a minimum value from where it have to find the signals. So we will assign a minimum value which is 16 here, that above 16 you have to find the signal. So it will find the signals, these two signals only. Otherwise if we assign a signal minimum signal 10, it will get all these signals. So it will be creating a very bad fit. If we assign a signal value above 16 or let us say above 18, which will be fine, it will be only getting these two peaks, right. So that will be fine. So it will be very good to fit the values. So the mean of those fits, those peak will be the actual value of the observed redshift, observed lambda, sorry, and that observed lambda can be used to get the actual value of the redshift. Okay. So let's do the things. Let's say flux underscore peaks will be is equals to ss, the signal, scipher dot signal, find peaks. So this is a function for that, and the sub values, sub flux. In the sub flux, the sub flux will be greater than the height. Height will be is equals to 18. Okay, and index is equals to 0. The minimum height guess, basically minimum height guess for the peaks. Okay, and now the means will actually give us the two values. Those two value will be for one this peak and one this peak. So it will be actually giving us the value of the wavelength. So we will be writing something in the terms of wavelength. So it will be giving us the value of the wavelength at which these peaks exist. So this will be something like sub underscore wave, and what for what values, the peak flux values. Okay, so it will be giving us the two values. So when I will just print means, so you see that we have the exact value of the observed wavelength. So we can apply the redshift formula, observed wavelength minus theoretical divided by theoretical. So we can get the redshift here. This is okay to calculate the redshift, but what about fitting the plot? So right now we have this easy method that we can assign it a height and get the actual value, but when we have the raw data, when we don't know anything about the wavelengths or that thing, we have to do exact fitting, right. For that fitting parameters, we have to just give it a guess. Now what will I do is, we will have to fit our model to get the exact or similar values of this. So our model, if our model is working fine, the wavelength 1 and wavelength 2, the mean values must be nearby these actual values, these exact values. So we will try to test. So the main part was of today's lecture was to create and learn how to create the model which can fit into some profiles, Gaussian profiles. So not every time we will have these exact values. So sometimes we have to put some guesses and we have to find those kind of values. Okay, so these values we just calculated is just for reference, that are even is our model correct or not. Okay, so this doesn't work every time. Okay, so now what I will write, I will assign some different values, of matrix underscore, let us say, and we will call that fit function, and subwave comma sub underscore flux comma, let us say 25 and let us say 20, and our mean guesses will be, let us say, these two mean guesses, or otherwise you can just apply for H alpha, or you can just make it a guess around that. So our guesses will be multiplication of those means comma 1 comma 5, because we have the theoretical spectrum, right. So we can use also that thing. So since our model is not that much strong, so it's just a two simple Gaussian plots. It's not a very complex Gaussian model, right. So we are giving it the guesses near to this, because for the complex model we have to add some more parameters. So we have to write a multi Gaussian model thing kind of there. So this is for fitting model to real spectrum. So let's finger cross and just run this. Okay, so you see it tried to fit the model. So you see our data was so funky, it was somewhere up and somewhere down. but it tried to fit our model, and it's very good, very good. And you see the wavelength values are very very near. The second wavelength fluctuate a bit, like it is 7209, but its actual value is 7211. So it's fine, it's not that much variation, but it's okay because we also got the error 0.2, so that actually worked very fine. So these are two values we got very perfectly, and our model is fitting very perfectly. So this is how you work with this thing. So this is actually the end of this session, but we are left with one thing, which is basically calculating the redshift, right? So we have not calculated the redshift. So now I think it's up to you to calculate the redshift, right? Because we have the observed values, and we have the theoretical values, but where is the theoretical value? So you have to see, is it H alpha or nitrogen doublet, because H alpha and nitrogen doublet are very close together. Okay, so or you have to look into this, which peak is this, and you will have to search for the theoretical value for H alpha and nitrogen doublet. So the H alpha value is 6562.8, I guess, and for the nitrogen value is 6583. So these are some journal values, you can remember it because it is very useful. So just write a function for redshift and put those values and put these mean values. So now I think that when you will write the formula, you will not print these values by copying these values, but you will print these values by using multiplying means. Okay, so I think that you can use the indexing at these means, like in mean index 0 will be the r lambda observed value minus lambda theoretical value by theoretical value. So you can just try to explore these things, how you can do the calculation differently, rather just giving it the value by copying from here, right? So this is how we use Gaussian profile to fit our spectrum. Okay, so this was the end of today's lecture. So I'll stop the recording here. First I'll save this file here. So I'll just stop the recording, and if you have any doubt you can ask now.